Hello, everyone, and welcome to the OneClass channel. My name is Donna and I'm a recent master's graduate from the Material Science program from the University of Ontario Institute of Technology, also known as Ontario Tech University. So today we're going to go over some commonly asked questions in chemistry at the high school, college, and university level. So if you needed any help with homework or tutoring, then check out the links in the description below. So now let's get started on our set of questions for today's session. Okay, so question 1 asks, what does the excited electron configuration represent? Okay, so the excited state of an electron is when an electron temporarily occupies an energy state that is greater than its ground state. So it occurs when it either absorbs a proton or when it collides with a nearby atom or particle. So an example is when an electron goes from its ground state at n equals 1, and then it can jump to a higher energy state, let's say n equals 4. Okay, so let's see what the junior tutor said. The excited state electron configuration shows the configuration of an element whose valence electron has gained energy to move from a ground state orbital to an orbital in higher energy level. Yep, so this solution is correct. Okay, so on to question 2, which asks to draw the neutral organic product for the reaction shown below. Show the stereochemistry of the product. Okay, so let me just first write down our reactant. So this is just an alkyne molecule because it has a triple bond. And it reacts with like this lithium metal complex. And ammonium chloride. Okay, so what happens during this reaction is that our alkyne is reduced to a trans alkene. So when we have a trans alkene, this is when our substituents are on opposite sides of a double bond. So I'll draw out the mechanism to show how the reaction takes place. And this happens with a very strong reducing agent. So, and the catalyst which is lithium metal. So the ethylamine solvent is our reducing agent. Okay, so I'll draw the first step of the mechanism. So notice these are half arrows, which indicates that only one electron is being transferred. So in the first step, lithium has a single electron. Well, yeah, single valence electron. In its valence shell. And it can readily donate to the alkyne. To form a radical intermediate. So radicals are very unstable, and it'll just look like a single electron on one of our carbons. So I'll draw the intermediate down here. And that is our newly formed radical. The triple bond is now a double bond. And we have a negatively charged carbon that is stabilized with the lithium right now. And then I'll just draw our ethylamine up here. And this negatively charged carbon will come and deprotonate the amine. give us another intermediate. And then another lithium. So our second mole of lithium comes in to help stabilize this radical. So I think it just donates one of its electrons to the radical. Draw a single half arrow. Sorry. And then our next structure has that same like negatively charged carbon. Okay, so now we have kind of a similar structure to our other intermediate. And now this carbon comes and deprotonates another ethylamine. Which gives us our final product. And then notice that our structure is in the trans position. So meaning the two substituents, so that's cyclohexane and that isopropyl group are on opposite sides. Okay, so let's see what the junior tutor said. The reaction above shows an alkyne. The reactions of alkyne typically center on the triple bond. The reagents given suggest that what would happen is an addition reaction, more precisely an anti-addition of H2. This would result in a product that would have a trans configuration. The product is trans 1-cyclohexyl 3-methyl-but-1-ene with the structure below. Yep, so the solution is correct. Okay, so on to question number 3. How many pints to a quart? There are, in fact, 2 pints in 1 quart. So pretty straightforward conversion, and the junior tutor said the same thing. So this solution is correct. Okay, so question 4 asks, what are the resonance structures of the peptides shown below? Okay, so let's draw out our peptide. So this is one amino acid with an R group that is just CH3. So I believe that's alanine. And then this is our second amino acid in the peptide, which just has an R group equal to H. So it's the simplest amino acid. I believe that's glycine. It's been a while since I did biochem. But anyways, this is our peptide. And to draw our resonance structure, I'm just going to show the movement of electrons from the lone pair of this amine group and come down to form a double bond, leaving the carbonyl group to have a negatively charged oxygen. So now this nitrogen has a positive charge, and everything else just stays the same. Okay, so this is one of the resonance forms from this peptide. So let's see what the junior tutor said. The peptide is alanyl glycine, Ag. The peptide is in its Zwitter ion form, but this would not affect the resonance structures of the peptide. Resonance is centered on the peptide bond, which is shorter than the typical amide bond. The resonance of the peptide is shown below. Yep, so they show the lone pairs on the nitrogen coming down to form a double bond, and then the carbonyl comes up to form a singly bonded, negatively charged oxygen. So this solution is correct. Okay, so on to question number 5. What does the R stand for in the ideal gas law PV equals nRT? So the R is actually a constant. So it can stand for the ideal gas constant. And I'll show how we get its value. But first, I'll just define all the other variables in the equation. So P stands for pressure. And at a standard atmosphere, the pressure is equal to 1 atm. The V is for volume. So the molar volume is equal to 22.4 liters. And N is number of moles. So we are going to sub in 1 mole. And then lastly, T is temperature. So in standard conditions, the temperature is 273.15 K. And this is 0 on the Kelvin scale. Sorry that. Okay, so now that we know all of our different variables and all of their values in standard temperature and pressure conditions, let's rearrange the equation to solve for the value of R. So R then is equal to PV over NT. So now I'm just going to sub in our values to show how all the units of R come to be. Okay, so if we divide this all out, we end up getting an R value that is equal to 0.08206, and its units are in liters times ATM divided by moles times Kelvin. Okay, so the junior tutor said the R in the ideal gas equation is the ideal gas constant. The ideal gas constant has many values depending on its units, so that's also a good point. And typically the ideal gas constant is 0.08206 liters times ATM divided by mole times Kelvin. Yep, so this solution is correct. Question 6 says to classify each salt as an acidic salt, a basic salt, or a neutral salt. So first, let's define each of the different types of salts. So we can have an acidic salt, and this is formed when a strong acid reacts with a weak base. We could have a basic salt. This is when a strong base reacts with a weak acid. And lastly, we could have a neutral salt. And this is when a strong acid reacts with an also strong base. Okay, so let's look at all our different salts that they give us. They first have potassium nitrate. So potassium nitrate was formed using nitric acid, which is a strong acid, and potassium hydroxide, which is a strong base. So therefore, this is a neutral salt. Okay, so B, sodium hypochlorite. This was formed with hypochlorous acid, which is a weak acid, with sodium hydroxide. So this is a strong base. So therefore, this is a basic salt. And lastly, they have ammonium. I think this is supposed to be ammonium chloride. So this was formed from HCl. So hydrochloric acid is a strong acid. Plus ammonia, which is a weak base. So therefore, this is an acidic salt. Okay, so these are the three different types of salts. So the junior tutor said, to determine if a salt is acidic, basic, or neutral, we need to consider the following. When a strong acid reacts with a weak base, salt is acidic. When a weak acid reacts with a strong base, the salt is basic. And when a strong acid reacts with a strong base, the salt is neutral. So for potassium nitrate, it is a reaction from nitric acid, a strong acid, and potassium hydroxide, which is a strong base. Therefore, it is neutral. Yep. And then for the sodium hypochlorite, it is a reaction from hypochlorous acid, a weak acid, and sodium hydroxide, a strong base. Therefore, it is basic. For the ammonium chloride, it is a reaction from HCl, a weak acid. Well, I think they mean a strong acid. And NH3, a weak base. Therefore, it is acidic. Yep, so this solution is correct. I'm just going to clarify that it probably is ammonium chloride, formed from HCl, a strong acid, and NH3, a weak base. Therefore, it is acidic. Okay, so question 7 just states what is the molar volume of a gas at standard temperature and pressure? Okay, so first let's look at the ideal gas law. Okay, so in standard conditions, the pressure is 1 atm. The V stands for volume, and its units are in liters. N is number of moles. So we're going to sub in 1 mole. R is the ideal gas constant, equal to 0.08206 and liters times atm over mole times Kelvin. And the temperature will sub in as 273.15 K, which is 0 on the Kelvin scale. Okay, so now let's solve for the molar volume by rearranging the equation to get volume is equal to nRT over pressure. So let's sub in all of our variables. Number of moles was 1. The R constant, we are going to use 0.08206. Since we are working with these units. Temperature 273.15 Kelvin. All divided by the pressure, which is 1 atm. Okay, so notice that our units should cancel out to get liters. So our moles will cancel out here, our Kelvin will cancel out, and then our atm cancels out as well. And we are left with a value of 22.4 liters. Which is called the molar volume. So the junior tutor said, molar volume indicates the volume 1 mole of gas takes up at standard temperature and pressure, which is 1 atm and 273.15 Kelvin. This can be solved using the ideal gas law, which is mathematically expressed as PV equals nRT, where P is the pressure, which is equal to 1 atm, N is the number of moles, which is equal to 1 mole, R is the ideal gas constant equal to 0.0821, and T is the temperature, which is equal to 273.15 Kelvin. Dividing both sides of the equation by pressure and substituting the values, we have 22.4. Therefore, the volume of gas at standard temperature and pressure is 22.4 liters. Yep, so this solution is correct. I'm also going to add in the value of our R constant, which is 0. Just in case people didn't know, 0.0821 liters times atm divided by moles times Kelvin. This solution is correct. And on to question 8. How would you find the molar enthalpy of vaporization for a substance given 3.21 moles of the substance absorbs 28.4 kilojoules of energy as heat when the substance changes from a liquid to a gas. Okay, so let me define the molar enthalpy of vaporization. So it can be denoted as delta H vap So this is the enthalpy needed to convert from a liquid to a gas or a substance. So the heat needed for this reaction can be expressed using an equation where Q is equal to N times the delta H vap. So like I mentioned earlier, Q is for the heat and N is for the number of moles in the substance. Okay, so notice that the heat that is absorbed depends on how many number of moles of the substance that you have. And if you divide Q by the number of moles, then we can get the delta H vap of a particular substance, which will be the same no matter how many number of moles you have. So let's rearrange this equation so that we can solve for the molar enthalpy of vaporization for this particular substance. So we'll rearrange it so that it is delta vap is equal to Q divided by N. So now let's sub in the values that they gave us in the question. So it is 28.4 kilojoules. Oops. And then divided by the number of moles, which is 3.21. Okay, so this gives us a molar enthalpy of vaporization equal to 8.85 kilojoules per mole. Okay, so let's see what the junior tutor said. The molar enthalpy of vaporization of a substance is the enthalpy needed to change the liquid phase into the gas phase of the substance. The heat needed is given by Q equals N times delta H vap, where N is the number of moles present in the substance, while delta H is the vaporization enthalpy change for the substance. If given that you have 3.21 moles of the substance and heat it up to 28.4 kilojoules to change it to a gas, The computation will be delta H is equal to Q divided by N. Substitute the given values and solve. So delta H is equal to 28.4 kilojoules divided by 3.21 moles, give us 8.85 kilojoules per mole. A 3.31 moles of substance that absorbs 28.4 kilojoules of energy has a delta H equal to 8.85 kilojoules per mole when changed from a liquid into gas. Yep, so this solution is correct. Okay, so question 9 asks, how do you find the molecular formula? Okay, so there are different ways that we can find the molecular formula, but I'm going to give an example. So I'll make up an example question. So let's say that 2.78 milligrams of ethyl butyrate was combusted and 6.32 times 10 to the negative 3 grams of CO2 and 2.58 times 10 to the negative 3 grams of H2O were produced. Okay, so we need to find both the empirical formula and the molecular formula of ethyl butyrate, and knowing how many grams of both carbon dioxide and water were produced, we can find the answer to this question. Okay, so ethyl butyrate is just made up out of carbon, hydrogen, and oxygen. So the first step is to find the mass of carbon that was produced after it was combusted. So we know the mass is 6.32 times 10 to the negative 3 grams. And then we are going to find the number of moles of CO2 by dividing this mass by the molar mass of CO2, which is 44 grams per mole. Okay, so this gives us our moles, which is 1.44 times 10 to the negative 4 moles. And now we want to convert this to the moles of carbon. So there is 1 mole of carbon and 1 mole of CO2. And then to find the mass of carbon, I'm going to multiply by carbon's molar mass, which is 12.01 grams per mole, to give us a value of 1.72 times 10 to the negative 3 grams of carbon. So this is how much carbon that was produced, or that was in the original ethyl butyrate sample. Okay, so now we can do the same thing, but this time finding how much hydrogen was in the sample. So we know the mass of H2O that was produced was 2.58 times 10 to the negative 3 grams of H2O. We are going to divide by the molar mass of H2O, which is 18 grams per mole. So this gives us number of moles equal to 1.43 times 10 to the negative 4. Okay, so now we are going to find the mass of hydrogen that was produced. So to convert from the moles of H2O to the moles of hydrogen, we know that there are 2 hydrogen atoms in 1 water molecule. So this time we multiply by 2. And then we are going to multiply by the atomic mass of hydrogen, which is 1.01 grams per mole, which gives us a final mass of hydrogen that is equal to 2.90 times 10 to the negative 4 grams. Okay, so the only element that is unaccounted for is our oxygen. So since oxygen is in both CO2 and H2O, this is why we do oxygen last, because we know that the remaining grams that are left in the sample are just from oxygen. So all we need to do is convert the total sample of ethyl butyrate to grams. So it is 2.78 times 10 to the negative 3 grams. And then we are going to subtract the masses of both carbon and hydrogen that we solved in the previous steps. So minus 1.72 times 10 to the negative 3 grams. So this is our carbon. And then we're also going to minus 2.90 times 10 to the negative 4 grams, which is our hydrogen. And then we end up getting a mass of oxygen equal to 7.70 times 10 to the negative 4. Okay, so now we know all of our masses of each carbon, hydrogen, and oxygen. So now we're just going to convert to moles. So for carbon, 1.72 times 10 to the negative 3 grams. To find its number of moles, we just divide by its molar mass, which is 12 grams per mole, to give us 1.43 times 10 to the negative 4 moles of carbon. Then for hydrogen, it is 2.90 times 10 to the negative 4 grams. divided by hydrogen's molar mass, which is 1.01 grams per mole, which gives us 2.87 times 10 to the negative 4. And then lastly, for oxygen, it is 7.70 times 10 to the negative 4 grams, divided by oxygen's molar mass, which is 16 grams per mole, to give us 4.81 times 10 to the negative 5 moles of oxygen. Okay, so I'm going to start a new page. I'm running out of space. So I think this is question 9. And I forgot to add this in the question, but typically when we solve for molecular formula, the molar mass of the sample is given. So the molar mass of ethyl butyrate is equal to 115 grams per mole. So this will help us in calculating the molecular formula, but I'll get to that step in a bit. Okay, so now that we know all the number of moles of carbon, hydrogen, and oxygen, we divide each of them by the lowest value. So let's look at all the moles values real quick. And you notice that oxygen has the lowest number of moles, which is 4.81 times 10 to the negative 5. So first, let's find our empirical formula. The number of moles of carbon was 1.43 times 10 to the negative 4. For hydrogen, it was 2.87 times 10 to the negative 4. And then for oxygen, it was 4.81 times 10 to the negative 5. Okay, so now let's divide by the lowest number, which was for oxygen. So we're dividing everything by 4.81 times 10 to the negative 5. Okay, so this gives us an empirical formula equal to C3H6O. Okay, so now to solve for molecular, we need to find the molar mass of our empirical formula. So to do this, it is 3 times the molar mass of carbon plus 6 times the molar mass of hydrogen plus the molar mass of oxygen. So the molar mass of carbon, 12.01. Molar mass of, I read a 6 there. Hydrogen is 1.01 grams per mole. And then oxygen is just 15.99 grams per mole. So the molar mass of our empirical formula gives 58 grams per mole. Okay, so we know that our molar mass of ethyl butyrate is 115. So we need to divide 115 by our empirical molar mass, which is 58, to get the ratio of the two. So let's do 115 grams per mole divided by 58 grams per mole gives us 2. So therefore, we need to multiply our empirical formula by 2. So this gives us C6H12O2. And this is how we find the molecular formula. Okay, so let's see what the junior tutor said. To find the molecular formula, find the empirical formula first. Then from the empirical formula, get the empirical formula weight, and then divide the given molecular weight or molar mass by this. Lastly, multiply the ratio you've obtained to each of the subscripts in the empirical formula to get the molecular formula. To illustrate this process, let us work on an example. A sample of compound with a molar mass of 30 grams per mole, I'm assuming, contains 6.444 grams of boron and 1.803 grams of hydrogen. What is its molecular formula? Okay, so they gave us the mass already, so we don't need to solve for anything of the masses, so we just need to find number of moles. So for boron, they just divided 6.444 by boron's molar mass to get 0.59 moles. Number of moles of hydrogen, 1.803 divided by its molar mass, and it got 1.789 moles. And now the number of moles will be in the subscripts, and then divide them by the smallest value. So in this case, the smallest value was the number of moles of boron. So they divided both by the 0.5960. And then they got the empirical formula, which is BH3. And now they found the empirical formula weight. Yep. And then they divided the molecular weight by the molar mass of the empirical weight to get 2.2. So every time you have like a decimal, we want to round it off to the nearest whole number. So in this case, this is rounded to 2. And now we multiply the ratio to the subscripts of each of the atoms in the empirical formula to determine the molecular formula. So that's how they got B2H6. So this solution is correct. Okay, so number 10 just asks for the molar mass of magnesium. It can just be found on the periodic table, which is equal to 24.305 grams per mole. And the junior tutor said the molar mass of magnesium is 24.305 grams per mole, which can be found in the periodic table as atomic weight / mass. So the solution is correct. I think we have time for one more quick question, which just asks, how many pints are there in a quart? So there are just 2 pints in 1 quart. And the junior tutor said the same thing. Use the conversion factor 2 pints over 1 quart to solve for the number of pints. Yep, so the solution is correct. So that is all the time we have for today's session. And if you enjoyed today's Q&A and you'd like to be notified of when we do this next, please hit the subscribe button and notification bell below. If you'd like to submit a question of your own, then check out the links in the description. And also don't forget to leave a like and a comment if you enjoyed today's video. And don't forget to share with your friends and classmates if they needed any help with chemistry. This has been Donna from OneClass, and I hope to see you soon. Bye.